Topic 8.2, connecting position, velocity, acceleration of functions using integrals. So we did a lot of particle motion in the first semester, but we only did things involving derivatives. Hopefully you recall some of our discussion about the concept of particle motion from Unit 4 last semester. Now we've added the ability of using integration to our toolbox. We can do so much more with this idea. Recall in our study of particle motion, a particle moves along a horizontal line, so its position at time t is greater than or equal to 0, is given by the function s of t. Sometimes we call it x of t. It really could be anything, but usually we say s of t or x of t. Velocity, we do v of t, and acceleration is a of t. All right, a real basic one to start off with, just to remind us of what we're doing here. Your teacher moves along a straight line in the front of the classroom according to the values in the table below. Time is measured in seconds, x of t is measured in carpet squares. How far was your teacher's ending position from his starting position from t equals 0 to t equals 4 seconds? This question is simply asking about displacement, ending position from starting position. The fancy math word for that is displacement. So ending position minus starting position is 16 carpet squares. What is the distance your teacher traveled from 0 to 4? This is talking about total distance traveled. This is not displacement. So this one we got to break down individually every time we change directions. So the first, from 0 to 1, we moved 4 squares to the left. And then 2 squares right, 2 squares right, and 16 squares right. So 2, 2, and 16 for a total of 24 carpet squares. So even though we traveled 24 squares, we only ended up 16 squares away from where we started. That's the difference between distance versus displacement. If you don't have your calculator handy, go ahead and get it out now. Pause the video if you need to. And when you're ready, go ahead and type in v of t into y1. I'll be doing the same as well. So v of t is t minus 3 ln t minus 2. Obviously, in your calculators, you should be using x instead of t. But when you hit the x button, the x will simply show up. Okay, as always, make sure you're in radian mode before we go any further. And now let's take a look at what this question is asking. It is known that s of 0 equals negative 3. So our starting position is negative 3. It's probably going to be pretty important at some point in this problem. Question A. Find all the values of t on the interval for which the speed of the particle is 5. Okay, so we want to know, when will the velocity be 5 or the velocity be negative 5? Okay, because speed is the absolute value of velocity. So what we're going to do here is we're going to graph this between the window of 4 and 7. Now you can open that window up more if you want to. You can go 0 to 10 if you want to, or whatever. As long as 4 and 7 are inside your x bounds, you're in good shape. The y bounds, it doesn't really matter as long as you can see your graph. That's really all that matters. And what we're going to do here is we're going to set y2 equal to 5 and y3 equal to negative 5. All right, and then we're going to take a look at this graph. So I'm just going to draw a little picture of what this graph would look like. Over here. All right, so we have t minus 3 ln t plus 2 plus 2t sine t squared over 12 as our function. My graph is slowly popping up on my calculator screen. All right, it looks something like that. All right, again, we're looking, when will the graph be 5 or -5? Only between 4 and 7. All right, so now on your graph screen, we are trying to find these points. But again, only these points if they're between 4 and 7 for t. Okay, so if you go to second, calculate intersection, and if you scroll over to our first one, which is all the way over here, and hit enter on that a few times, you're going to get 3.6. So that is not in our interval, so that one does not count. All right, so let's do this again. Scroll over to the second one. And we get 5.621. That is an answer. So our first answer is about 5.621. All right, and then just do that again. So second, calculate intersection. Scroll over to the next one. We get 6.520. So 6.520. Scroll over to the next one. And we get an answer that's 8.4. So we know that's out of it. This one here is 8.4, which means the next one is also out of our range as well. So just two answers, 5.621 and 6.520 seconds. The speed will be 5. Part B, write an expression involving an integral that gives us a position s of t. Use this expression to find the position at time t equals 3. This is our accumulator function that we worked with a lot in chapter 6. So our position is going to be our starting point, which is -3, plus the integral from 0 to t of v of x dx. Now remember, when we did this, you can't have this variable matching this variable. All right, so since we're looking at time t, you have to change this variable to anything you want. I chose x, but you can choose whatever you want. Okay, so now we're in our calculator. Go back to the home screen and simply type in -3 plus the integral from 0 to 3 of y1 dx. And we should be getting -6. So s of 3 is -6.263. That is its position. 6 units to the left of the origin. Part C, find all the times t in the interval 0 to 8 where the particle changes direction. Justify your answer. So all this is when will the velocity be 0? So go back to your graph. And let's see when the velocity hits 0 between 0 and 8. So for this one, I would definitely change my window to 0 to 8, if you haven't already. And my graph is coming up here. It looks like there are 2 times where the velocity changes from negative to positive or positive to negative. The first one, so go to second, calculate 0. Scroll over to the first one, which is a little after 2. And it looks like I'm getting 2.341. And there is one more, so let's get the next one here. So another 0. Scroll all the way over to the next one, and we should be getting 6.127 seconds. Okay, why is that happening? Because the sign of VT is changing. So V of t changes signs at these times. Okay, last one of these. Question D, is the speed of the particle increasing or decreasing? Okay, so for this, remember we got to find the velocity and the acceleration at that point. So we got to find V of 7 and A of 7. So V of 7 you can just hit vars, y vars function y1 of 7, and we get negative 10.912. Or you can actually do it in the graph as well. And then for the acceleration at 7, go to math number 8, derivative of y1 at 7. And we get negative 10.561. Since both of them are negative, which really all that matters is that they're both the same sign, the speed is increasing. So increasing since v of 7 and a of 7 have the same sign. It doesn't matter if they're both positive or both negative, as long as they're both the same. So next slide, this is just a table. I strongly encourage you to look this table over, study it, read it, make sure you understand whatever it means. This side would be what you'll see in a problem, and this side is what you should be thinking when you see that. But we're going to move on here to the next problem. Example 2, Space Shot. The Space Shot is an amusement park ride that gently raises riders up a tower and then rapidly bounces them up and down using compressed air. The velocity of the space shot for 0 to 14 is modeled by a piecewise linear function as shown below, where t is measured in seconds and v is in feet per second. So important to know, this is the velocity of this ride. At what times on the interval does the space shot change direction? Give reasons for your answer. So again, we're just talking about when does the velocity change signs. Okay, that happens at t equals 6, 8, and 10 seconds. And why? Because v of t changes signs at those times. Question B, write expressions for the ride's acceleration, velocity, and distance from the ground that are valid for the time interval. All right, so its acceleration from 10 to 12, we're looking at this small little piece right here, is just going to be the slope of that line. So it's going down 20 over 1, down 20 over 1. So the acceleration is just negative 20. So a of t is negative 20. The velocity is just the equation of that line. Just the equation of that line. So it's negative 20. And we can put a point in there. So our slope would be negative 20. And the point we can pick would be, how about 10 comma 0? So we'll just set it up as in point slope form here first. So y minus 0 equals negative 20, x minus 10. We'll convert this to what it actually means here in a second. So there's your equation. That's the velocity. So that's going to be v of t equals negative 20t plus 200. Did you have to use the point 10 comma 0? No, you did not. You know, there's other points on here. You could use 11 comma negative 20 or 12 comma negative 40. But anytime you can use a 0, it makes things a little bit easier. All right, and then for distance, s of t, so s of t would be its starting position, which we don't know what it is, but we can say s of 10, plus the integral from 10 to t of this function. Now remember, don't use the same variable. How about negative 20x plus 200 dx? Question C, what time in the interval is a space shot the highest? How high is the ride at that time? Let's go back to our graph here. We're looking for a maximum. We're trying to optimize this. What is the maximum? What two places where maximums can occur? Endpoints or critical points. So it could be at t equals 0, it could be t equals 14, it could be 6, it could be 8, it could be 10. Except one of those we can clear out right away. It's definitely not at t equals 8, because that's a relative minimum. The graph of velocity is changing from negative to positive there, which means the position would have a relative minimum at that point. So our four candidates are 0, 6, 10, and 14. So let's make a little table of t and v of t. Sorry, S of t. And we're going to have 0, oh, I can't remember what they were already, 6, I think, 10, and 14. 6, 10, 14. All right, so the height of 0, well, that's obviously going to be 0. So that's definitely not our highest point. The height at 6, we're going to use that integral that we just came up with on the last slide, but instead of doing that, we're going to go with 0 as our starting point. So it's going to be S of 6 equals 0 plus 0 to 6 v of t dt. All right, so finding the integral from 0 to 6, it's just a trapezoid here of height 20 and bases 6 and 5. So 1/2, 20, 6 plus 5. Should be 10 times 11. 110. And then for 10, we can start there. We can say S of 10 equals 110 plus the integral from 6 to 10 of v of t. Oh, wait a minute. I just realized that this is 4. This base is 4. Sorry about that. So that'd be 10 times 10 or 100. I should go back and change all these with me. All right, so 100 plus 6 to 10 v of t. Okay, so for this one, 6 to 10 would be 1/2, 2 times negative 60 plus 1/2, 2 times 40. Such as negative 60 plus 40, or negative 20. So this is 100 minus 20. The position at 10 would be 80. And then for our last one, we can go S of 14 equals 80 plus the integral from 10 to 14 of v of t dt. Let's go back to our graph one more time. That's going to be 1/2 times 4 times negative 40, which is 2 times negative 40, or negative 80. And then 80 minus 80 would be 0, which makes sense. At the end, the ride should probably return back to the ground. So what's the highest point? It'd be at 100 at 6 seconds. So if we wrote that out in a sentence form here, the space shot is the highest of 100 feet. Oh, that's a good sentence. At time t equals 6 seconds. Maybe the space shot reaches its highest height. Yeah, I don't know. Whatever you think is better for your English sentence. Probably not best to go with mine there. All right, last one with D. Write expressions find the total distance the space shot travels during the time interval 0 to 14. Okay. So the space shot changes directions here, here, here. So we got to find how much space it covered there, how much space it covered here, how much space it covered here, and how much space it covered here. We kind of already did that in the last one, right? So first of all, to find this, it's going to be distance is the integral from 0 to 14 of the absolute value of velocity. Okay, and we kind of already did this in the last one. All we're doing is adding these pieces together here. So from 0 to 6, we said that was 100. 6 to 8 was negative 60. 8 to 10 was 40. And 10 to 14 was negative 80. But it's absolute value. So all we're going to do is we're going to add those together. 100, 60, 40, and 80. 100 plus 60 plus 40 plus 80. So the total distance traveled would be 280 feet. Example 3, quick multiple choice question practice with particle motion. Question A, a particle moves in a straight line with a velocity v of t meters per second, where t is time in seconds. At 5, the particle's distance from the starting point was 6 meters. It was the total distance the particle has traveled between 5 and 10 seconds. Okay, so total distance traveled is the absolute value of velocity. And that's pretty much all we need here to know, because there's only one of these that has the absolute value of velocity written down, and that would be C. All right, total distance from 5 to 10 would be the integral from 5 to 10 of the absolute value of velocity. All right, A, I don't know what that would be representing. Nothing important, that's for sure. It's probably just 6 meters per second added to the particle's velocity in general. B would be the position at time 10, and then D would be the displacement at time from 5 to 10. So C is what we're looking for in this problem. Number 2, a particle moves in a straight line with velocity v of t, meters per second. T is in seconds. At 2, the particle's distance from starting point was 10 meters. What is the particle's displacement between 2 and 9? So displacement, remember, is just the integral of velocity. That's it. And there's only one of these that's just the integral of velocity, and that would be B. A would represent a position. C is your total distance traveled. And then D, I'm not really sure what that represented. It'd be a total distance increased by 9, which doesn't really represent anything important. All right, last example, example 4. Remember we talked about the NUT strategy, the noun, the unit, and the time. So we're just going to fill out this table here, and it would not be a bad idea if you would pause the video at this point and try to fill out this table on your own, and then come back when you're done. Try to fill in what each of these represent in terms of nouns, units, and time. Okay, now everything you probably need to read would be up here. Let's read that here first. The position of the particle moving on the x-axis in feet from the origin is given by x of t. The velocity of the particle in feet per second is given by v of t, and the acceleration is a of t. For each of the integral expressions given in the following table, interpret its meaning by filling in the n, u, and t. All right, so for the first one, again, if you want to try this on your own, it'd be a good idea. Go ahead and pause the video here. But if not, we'll go through this together right now. For the first one, x of 2 plus the integral from 2 to 4 x prime of t dt. All right, this is going to represent the position at time 4 seconds. All right, so the noun would be the position of the particle. The units, well, the units for position is just given by feet. Okay, it's feet from the origin, just feet, and t equals 4 seconds. Second one, the noun would be the displacement, or you can say what it says here, the change in position of the particle. Units is still feet. And this is time from t equals 1 to t equals 4 seconds. The third one, this is an average value function. Average value of what? Average value of the absolute value of velocity, which is the average speed. So this is the average speed of the particle. Okay, speed is feet per second, and the time is, again, from 1 to 4 seconds. The fourth one, x of 4 plus the integral from 4 to 2. That's the position again. So that's very similar to the first one. It's the position of the particle, this time at t equals 2. at time t equals 2 seconds, and given in feet from the origin. The fifth one, that is just the total distance. All right, so that is the total distance traveled by the particle. That again would be in feet, and that's from t equals 1 to 4 seconds. And the last one, it's an average value function again, so it's the average acceleration of the particle. Acceleration is given in feet per second, or feet per second squared. And once again, this would be from t equals 1 to t equals 4 seconds. All right, that will do it for the screencast for today's lesson. Hope you enjoyed it. Thanks again, and we'll see you again soon.